Welcome back everyone. In this lecture we will continue with the Fourier analysis on general finite non-abelian groups. So, before proceeding to the non-abelian groups, let us recall what we have done for abelian groups. Then we will actually take that as our motivation and then try to replace certain spaces so that we can actually do the Fourier analysis. So, here we start with let us say finite abelian groups and then see what we did so far. So, this is finite abelian group. So, recall that the G hat this is the dual group which is the one dimensional characters from G to C cross. So, indeed the Fourier transform was defined from the C G to C G hat. You take a function f and then send it to this f hat. So, the f hat of chi defined to be the cardinality of G times the inner product f comma chi. So, this is how we define the Fourier transform. So, now this interpretation actually kind of not going to help us much. So, we need to actually replace the dual group by something else. So, if we replace this G hat by again the group characters, so then that is not going to help us. The main realization is that this G hat indeed gives us set of irreducible irreducible representations of G hat. So, G hat is indeed can be identified with the set of irreducible representations of G. So, the best thing to do is replace G hat by the set of irreducible representations and then we need to consider functions on the representations. So, that will be the best thing to do. Okay. So, but before that let us closely understand what happened to this function space from G hat to C. So, indeed if we think about it the Fourier coefficients kind of recover completely the given function. So, instead of actually recording this f hat one can also record all possible Fourier coefficients. So, what does it mean? So, I can actually replace G hat by something else. So, as follows, you take C G and then you have this C G hat. Now, what we do? We just simply replace C G hat by this C direct sum n. So, what I mean by that? So, you take f, we are actually saying that Fourier transform actually takes f to f hat. But instead of recording f hat, one can also record f hat of chi 1 etcetera chi n. Okay. So, let us fix chi 1 etcetera chi n. This is the set of one dimensional characters of G, set of irreducible characters of G. So, now what we do, like instead of recording f hat as a function, we can also record this as a tuple which takes this f hat of chi 1 and so on etcetera f hat of chi n. So, what is this f hat of chi, which is by definition the cardinality of G inner product f comma chi. As we noticed before, the inner product completely recovers f, okay, that is what we keep telling. So, the same isomorphism can be actually replaced with this new map. So, now it is not very difficult to see this new map is indeed an isomorphism of vector spaces. Okay. So, this composition T dash is a map from C G to this C direct sum n. This is an isomorphism of vector spaces. But at the level of T we had actually isomorphism of C algebra. So, where the Fourier transformation actually taken the convolution product into the pointwise product. Okay. So, then if you think about it similar pointwise product can be defined here as well in C direct sum n. So, now using that pointwise product one can make this C direct sum n into C algebra. So, then one can see that under that pointwise multiplication and pointwise addition. So, this C direct sum n becomes C algebra and this composition is indeed becomes C algebra isomorphism. That is because T dash is indeed C algebra isomorphism, that is easy to see because we have taken pointwise multiplication on C g hat. So, now this is isomorphism and this is isomorphism implies the composition is an isomorphism. So, indeed what we did we have replaced this C valued function from g hat to this the value of the inner product of f and chi, okay, where chi varies over all g hat. So, that interpretation in somewhat motivates us to actually look for what will be the nice space on the right side. Okay. So, indeed one can see that all irreducible representations of finite abelian groups, they are one dimensional. So, instead of actually looking at it as okay, this inner product f and chi. So, we can see that basically the function f, if you want to keep track of that function. So, what one can do, one can see how that function takes actually values along with this irreducible character. So, maybe let me just write down the formula and then it will become clear what I mean by that. So, one can replace f hat as follows. So, if you take f hat of x, okay, so sorry, f hat of chi. So, this is what we define it to be the inner product f chi with the weight cardinality of g. Now, if we think about it, what is the inner product f chi? The inner product f chi is 1 divided by the cardinality of g summation f of x chi of x bar x in g. Okay. So, since chi bar corresponds to the dual representation. So, if we rewrite this here, we can also record f as follows. So, f of chi star is indeed equal to, okay, maybe let me keep it as chi only. F of chi is indeed equal to summation f of x chi of x bar x in g. So, basically what we got here, so we are keep tracking the values of f, okay, along with the values of the representation. Okay. So, that is what this f hat of chi indeed keep tracking. Okay. So, here we have actually put chi bar, but if you vary over all chi, then indeed what we actually record is all possible this summation f of x chi of x only. Okay. So, to store, okay, to store the data f hat, it is enough to record this summation x in g f of x chi of x for various chi in g hat. Okay. That is what we have observed. Okay. Indeed, what Fourier transform does, Fourier transform indeed actually records all of them. But here all the functions are complex valued function. So, this summation actually makes sense. But what happens if we go to the general finite groups? So, we may not be able to actually have this luxury anymore. So, the only thing is the chi of x, it may not be complex valued. So, one replaces this chi by general representations. Okay. So, then it will take value in the endomorphism of that irreducible representation. So, that is the only thing that will be changed. So, note that this is indeed irreducible character, sorry, irreducible representation, not the character, irreducible representation. So, the same formula that we want to actually use it for the general groups. So, we want to write summation f of x phi of x x in G. So, basically my f hat of phi should be recording something like this. But where this f hat will lie, that is where the question, if we use this same definition. So, note that phi is a representation from G to let us say GLV phi. Okay. So, we take first of all phi to be irreducibles, because that is what happened even in the finite abelian case. So, we were working with the G hat which is irreps of G. So, that should be the correct space to replace. So, then the values is not going to be complex valued anymore. So, phi of x is going to lie inside the endomorphism of V phi, and this summation f of x x in G, that is also going to lie here in this endomorphism of V phi. So, basically we want to treat this f hat indeed of functions from irreps G to this endomorphisms, that direct sum of this endomorphism of V phi. Okay. So, let us make this very precise. So, where this Fourier transform is defined, that is the first question that we would like to answer. The Fourier transform, like I said, it is defined from, so given function, again function will come from CG. So, given this, we want to record f hat. So, where this f hat lies. So, this f hat indeed lies inside. So, each one of them you can see that so they are functions. So, basically you take it to be direct sum of the endomorphism of V phi, and phi comes from this irrep of G. Okay. So, now again, like what is the meaning of this f hat which is lying inside this direct sum. So, if you think about it, so we are not recording the function, we will record the coordinates. So, it is enough to say what is this f hat of chi. So, that is what I told you here. So, instead of recording f hat, you just record all possible f hat of chi. So, that means what is this f hat? So, this f hat is just the f hat of phi, where phi runs over all these irreps of G. Okay. So, it is basically tuple of matrices. Okay. If you fix basis for all these irreducible representations, then you can see that what we are considering is actually tuple of operators or tuple of matrices. Okay. So, let us make this thing more precise. Okay. So, if you are comfortable with this notation, then it is okay. Otherwise, we can also fix the basis of these irreducible representations and then work with the spaces of matrices. So, the analogy is that C direct sum n, where C is, you can treat that as 1 by n one matrix. Okay. So, C is indeed 1 by 1 matrix on C. So, naturally the irreducible characters which are like group characters, that is chi from G to C cross. So, this will be replaced by irreducible representations of G, and this space C will be replaced by the matrix space. Okay. So, this is the generalization that you go from finite abelian group to the general finite group. Okay. Okay. So, let us actually fix some notations and then do this very precisely. So, let us take G to be finite group, and then let us fix this phi 1 etc. phi s to be the set of unitary representatives of the equivalence classes of irreducible representations of G. So, we assume it to be unitary irreducible representations of G. Okay. So, that means they are unique representatives from the equivalence classes of irreducible representations of G. In particular, we know that S is nothing but the number of conjugacy classes of G, which is exactly the dimension of the center of CG. So, now what we will do, we will fix this matrix coefficients. So, denote dk by the degree of this representation phi k. So, which is exactly the dimension of V phi k. So, given this phi k, we can talk about its matrix coefficient. So, they are functions from G to C. Okay. So, there are exactly dk square numbers of functions. So, in particularly you can see that phi k of G is given by phi k I j of G, okay, that dk by dk matrix. So, we already know that these matrix coefficients they form an orthonormal set. You normalize. So, then what happens, square root of dk phi I j k. So, these matrix normalized matrix coefficients, they form an orthonormal basis for CG. Okay. So, this is form on orthonormal basis for CG. So, this is something we have already proved. So, that means, so if you are interested in recovering a function from G to C, so one can actually change the basis, and then we want to recover the function in terms of this basis. Okay. Basically, all we are doing is change of basis, which is also giving us this isomorphism between these C algebras. One is the CG, another one is this product of matrices. So, that is also called Vedabin theorem. So, maybe let me state it as Vedabin theorem. So, before that let us actually define what is the Fourier transform. So, the Fourier transform is defined as follows. This is Fourier transform. So, where is the space? This is again a map from T from CG. Now, what we do? We take this product of this matrix spaces. So, we take MD1 C cross etc. cross MDSC. So, this is analogous to that C direct sum C n times for abelian group G. So, now how we are going to record the information that f hat. So, given f, we define this f hat, where f hat is given by the tuples. So, you just take this f hat of phi 1, okay, etc. f hat of phi s. So, we are going to record this as this S tuple, maybe S linear operators, where what are these f hat of phi k. So, if you think about it, this f hat of phi k is given to be the summation f of x phi k of x, x runs over g. Okay. So, this is how we define this f hat of phi k. So, in other words, this can be rewritten as follows: f hat of phi k, which is by definition summation f g phi k of g, g in g. So, now if you use this matrix coefficients, this you can rewrite as summation. So, maybe let us look at the ijth entry, f hat of phi k, the ijth entry is going to be summation f of g phi ij k of g, g in g. Okay. So, this is the ijth entry of this matrix. So, which is an element of endomorphism of V phi, okay, or you can treat it as element of the dk of C. So, now this is, if you can see, this is exactly the inner product. So, this is inner product f comma phi I j k. So, with the multiplication by n. So, n is the cardinality of G. So, the Fourier transform of f is indeed recorded by all possible inner products between f and the matrix coefficients. So, then we want to say that basically the Fourier inversion holds here. So, given f hat, you will be able to actually recover entirely the f. Okay. So, let us actually state and then prove the Fourier inversion. So, here is the theorem. So, given f from G to C, complex valued function on G. So, then what we can do? We can actually recover f using its Fourier coefficients or the Fourier transform. So, f is recovered as follows: f equal to 1 divided by n summation I j k dk f hat of phi k and then I j, the I jth entry of that times phi I j k. So, basically we can rewrite f in terms of this summation dk f hat and so on. So, all we did is we have changed the basis. So, we are rewriting f in terms of this matrix coefficient basis with the coefficients given to be recorded by the Fourier transform of f. So, that means given Fourier transform we can recover f completely. So, the map that we defined gives us an isomorphism. So, this map is an isomorphism. So, once we prove this is injective, both have same dimension, the cardinality of G is exactly d1 square plus etcetera ds square. So, that implies that this map is indeed isomorphism. So, I will leave it to you to check that this is indeed isomorphism of vector spaces, because whatever that goes into the definition, they all indeed linear. So, if you use this interpretation, then it is clear that f goes to f hat is indeed linear in f. So, we get vector space isomorphism. Maybe we will check that it gives algebra isomorphism. So, that is the core part of the Wedderburn's theorem. Okay. So, now why this theorem is true, that Fourier inversion is true. So, let us start computing the coefficient using the orthonormality of this square root of dk phi I j k. So, you can see that if you use that, So, here is the proof. You write f equal to summation the inner product between f comma square root of dk phi I j k and then phi I j k. Of course, the square root dk will be there, square root dk, where I j k varies. So, now what is this? This is exactly given by the Fourier transform. So, by definition, so you can just multiply by n and then divide by n, and then you can also see that you can take out this square root dk. So, then what you get exactly, this is exactly equal to 1 by n summation I j k varies, and then you keep this phi I j k here, and then you see that whatever remains here, this is exactly n times dk inner product f comma phi I j k. So, that is exactly your Fourier transform, this n and this. So, this is exactly dk n times that inner product f phi I j k, which is f hat phi k I j, sorry, phi k of I j. Okay. So, this is more or less by definition that given f hat you can recover f. So, that means the map is injective, they have both same dimension. So, it is surjective. So, that comes for free. So, the only thing that remains to check is that the Fourier transform is an isomorphism of C algebras. So, I already told you it is an isomorphism of vector spaces. Now, to show that it is isomorphism of C algebras, we have to check it is a ring isomorphism. So, it is enough to check that T of A star B is given by T A times T B. Now, note that what is there on the right hand side. So, you have C G and then you have the product of the matrices, and since it is the direct product, so it is enough to focus on the particular coordinates. So, we need to check T of A star B is same as T A times T B. So, the product on the right hand side defined coordinate level. Okay. Suppose if I take A1 etc. AS and then B1 etc. BS. So, coming from let us say this R. So, then the product is defined to be just the pointwise product AI BI I range from 1 to S. So, that means to prove this ring isomorphism, so by definition of the multiplication we just verify the following. So, we just establish that so A star B hat applied on this phi k is same as A hat applied on phi k times B hat applied on phi k. So, it is enough to show this for all k between 1 to S. Okay. So, we are just doing it by coordinate wise. So, the computation is very much analogous to what we did for abelian case. So, you take A star B hat applied on phi k, which is equal to summation A star B of x and then phi x k bar x in G. So, this is by definition of the Fourier transform. So, okay, so we need to be little bit careful because we have taken the Fourier transform to be, okay, I have taken to be the bar. Yeah, let us go back to the definition and then see. The definition tells that I have taken this summation f of x phi k of x. Maybe to be consistent with the abelian case, what we can do, we can actually put bar here. There is no big deal. So, just to be consistent with the definition of abelian groups. So, one can take bar here. So, that means I can actually put a bar here and bar here. So, f hat of phi k, we take it to be summation f g phi k of g bar. So, now this f hat of I j phi k of I j will be that summation f g and then phi k of g I j bar. Okay. So, that means oh, this is the inner product already has the bar there. So, this equality is true only when you put the bar. Okay. Okay. So, now if we go back to our calculation, so I guess what we have here, this calculation is correct, there is no issue. Here I want to prove this, A star hat of phi k is A hat of phi k dot B hat of phi k. So, let us look at the definition. So, A star B hat of phi k is going to be summation x in g A star B of x phi x k bar. So, that is just by definition of the Fourier transform. So, now if we rewrite this, so this is going to be summation x in g phi x k bar summation. Now, we just use the definition of the convolution product, it is going to be A of x y inverse B of y, y comes from g. Now, this is equal to, if we just do little bit change of variable. So, we just rewrite, just change the summation y in g b y and then summation x in g A x y inverse phi x k bar. So, this is what we get. So, which is exactly equal to the following. So, what we do, we just do the change of variable. So, we write z equal to x y inverse. So, that means x equal to z y. So, if we just substitute this, so then we can see that the left hand side, which is A star B hat of phi k is going to be exactly equal to summation y in g B of y summation z in g A z phi z y k bar. Okay. All I did is just change the variable, this to z and then x changed to z y. Okay. So, now again if you rewrite, this is going to be summation y in g B of y summation. So, we just use the definition of this phi. So, note that phi is representation. So, phi of z y is going to be phi z phi y. So, that means this I can replace it by phi z k and phi y k. So, this is going to be A z phi z k bar and then phi y k bar, where z comes from g. So, now if we just closely look at it, I can take out phi z. So, I again interchange and then see that this can be written as summation z in g A z phi z k bar times summation y in g B of y phi y k bar. So, which is exactly A hat of phi k times B hat of phi k. So, this is what we wanted to check. So, that tells you that the map that we wrote here between these spaces. So, they indeed gives an isomorphism algebra. So, which is actually called the Wedderburn theorem in representation theory. Okay, this is actually we have proved the Wedderburn theorem. Wedderburn theorem actually is very much a general statement. So, we have proved it over actually complex numbers. So, here you can see that we have very explicit isomorphism given by this Fourier transform. So, now if you think about it, like if you are interested in recovering this f, so in order to recover f, so you just keep track of all possible inner product with irreducible representation. So, that way somehow you can actually recover this f, that is what it says. Okay, so I will stop here. So, this actually completes the discussion on Fourier analysis on finite groups. So, what I do, like in the next class, maybe I will give one application of this Fourier analysis to spectral graph theory. So, that will be kind of a very nice application. So, for all these lectures, like I am referring to this Benjamin Steinberg book. Okay, so you can actually look at that book if you are having any doubts. Okay, I will stop here. Thanks.